Today I will speak about okay. I will talk about micro-local sheaves. So this will be based on joint work as we have. So in many respects, this will be illustrations of several constructions that are explained on the previous lecture. So let me start and spend some time on motivation of what we wanted to do. And the motivation was to relate two types of examples of holomorphic symplectic algebraic symplectic varieties. The first type of examples is the famous quiver varieties of Nakajima. So they basically are generalizations of the modular spaces of instantons on certain four-dimensional locally Euclidean spaces. So inside the manifolds, such as we take C2 mod gamma and then the singularization of Klein and singularities. And the simplest example would be cotangent bundle to CP1. So really, from the real point of view, four-dimensional manifold, which desingularizes a quadratic cone, which is simply C2 modulo plus minus 1. So this type of symplectic manifolds is related to four-dimensional geometry, or D geometry. So more generally, so let me recall the framework of Nakajima, which I will then I will modify a little. So we start with the quiver gamma. Quiver simply means oriented graph. It has a set of vertices, I. It has a set of edges, or oriented edges, or arrows. So every edge has a source and target. So there are two types here, source and target. So, and we fix two types of vectors, two families of vector spaces. Vi, V, which is Vi, I, and W, I, vector spaces. And from the physical jargon is that those vector spaces is a space of colors, and this is a space of flavors. Okay. The terminology comes from quantum field theory, quantum chromodynamics. So this represents matter if you want matter fields, and this represents gauge fields. So what we consider, we form so the quiver variety M gamma of VW, and possibly there are some other line of data which let me not write them. Let me say it like this. It is modular space of diagrams diagram will be like this. So each arrow of the quiver, so if I have a quiver, it will be something like this. Will be an arrow H joining A and J, and each arrow will be doubled. So for each arrow from I to J, there will be two layers. AH, BH. So here let me write two arrows. For every H, I to J, there will be more things like this. This is in the mimics our original quiver, and then there is the spaces W. They are attached again in the one-to-one way to those WI, WJ. So they are connected with these, but they're not connected with themselves. It will be something like this: UI, VJ, VJ. They're required to satisfy certain conditions. First, there is the moment map condition. It's the algebraically the most important condition, means that for every I, you have sum over vertices H, which terminates at I. The target of H equals I will be AH. AH minus sum over vector H, which starts at I, will be BH. AH will be equal to UI. So this sum, so there are maybe several things like this. So sum of all of this minus the other is equal to going this way and this way. And in this examples related to instantons, there is this relates to the ITA kitchen infinite planet condition, for instance. So let me just say that in various versions there may be a constant here. So can introduce constant. It's a last constant. The first condition. And second, which I don't want to go too much, is some stability condition, just to form the modular space. Plus some stability. When I say modular space, I mean that we quotient by the group GLP, which is product GLPI, but we do not quotient by the group GLW, by anything with GLW. We get a variety with action on GLW. So GLW. So morally, this variety can be considered as a Hamiltonian reduction. So of the cotangent space of representations of gamma. So when you take the cotangent representations of gamma, naively is simply the product of for every arrow we have for every arrow in the quiver we have an arrow in the vector spaces. And in the cotangent space we take the arrow in the opposite way. So Hamiltonian reduction again by GL. Yes, I'm saying this kind of somewhat informal. So there is a particular case of this situation. So if we consider just this algebraic condition, if we fix its representations of certain algebra, so condition 1, representations of a certain algebra. And in particular, we'll be interested in the case and the quotient of this algebra when we assume that the W's are 0. So, particular case. This is more to this Hamiltonian reduction picture. So, when all Wi are 0. So, then we have the condition that this sum is equal to 0 because there is nothing there to go. So this is known as the pre-projective algebra. Sometimes we'll say this is PP of that. This is the first type of symplectic manifolds. And so as I say, they have this 4-dimensional flavor. Any discussion involves geometry or physics in 4 dimensions. And the other class of examples is purely 2-dimensional. It is modular spaces of local systems on Riemann surfaces. So more specifically, so Riemann surface is a little bit ambiguous term. It sort of assumes that we have a complex structure. So what I have in mind is just topological local systems. So we start with X being a compact oriented topological surface. We take G a inductive algebraic group. Over C. And we take the modular space, or more precisely, the modular stack of the G local systems on G. On X, sorry. LS. X. So modular stack. G local systems. So one can say naively that we consider just representations of the fundamental group into G, and to take the modular conjugation. So again, even in this situation, there are several ways of looking at it. So strictly speaking, this it is a stack because the quotient by the group, and also because this group has a relation. If you have a compact surface. So that this will be singular. So this thing is singular at reducible representations. So if you want to remain in the sort of realm of classical geometry, then we should consider irreducible local system, LS, irreducible G of X. It will be a smooth method. Otherwise, it will be a derived stack. So, and this thing has a symplectic form, symplectic structure, which is introduced by Goldman. Using the cut product. So symplectic structure. this means that we interpret the tangent space to the modular space by deformation theory, and it is certain H1. We can say the tangent space at a point P, point represented by P of LS G of X, equals H1 of X and R. And this is a bundle of Lie algebra. So now, if G is a reductive group, we fix an invariant scalar product. That's called XY on the Lie algebra G. And then we have the pairing, it will go like this. We have H1. So let me just write RP. Then H1 RP. And it would go into H2 of X, the coefficients in C, going by the formula, basically, how should I say it better, invariant scalar product like this, and then we'll also write it just for this, for the purpose of this formula, let me write it as alpha of X1. So this, more or less, the formula would be something like this. Would be, say, psi and eta would be right into alpha of psi cap eta. So we first look up product and then apply up. So here I'm cheating a little because this is not really, the fibers are not identified with the algebra, but they are identified under conjugation. And if you have an invariant scalar product, then it's okay. So in particular, for G equals GLN, we simply have E is a local system of vector spaces. So we have the pairing would go like this: H1 of X and E. The endomorphism of E would be simply this, and then H1 of X endomorphism of E. Here we can simply just the usual cut product with respect to associative multiplication. Here would be H2 of X endomorphism of E. The cut product. And from here I just do a trace H2. Trace H2 of X. So in this way, we get an anti-symmetric 2 form on the modular space. So it's not degenerate because of Poincare duality. So you get a non-degenerate. Non-degenerate because of Poincare duality. Anti-symmetric form. On LS, and if you want to keep in classical geometry, we'll just consider the irreducible part of X. And this somewhat less trivial, and that's proved by Goldman, which it is also closed. So in this way, we get a class of symplectic manifolds, which are purely in terms of two-dimensional geometry. Now, so in order to connect such things, I want to just discuss one other relatively general phenomenon. And this, sort of appeared a little in Maxim's talk at this conference. So, no. What do you call it? No, here I'm just saying that the fact that this happens comes from quantitative duality in category of homological dimension 2. In Nakajima theory varieties, it doesn't come from any category a priori of homological dimension 2. It may come from holomorphic geometry. Yes. So anyway, so what I want to say, let them also discuss, that there are, in fact, if you want to relate to such manifolds, that there are two different types of symplectic algebraic varieties. There are varieties, so to say, of additive type, and there are varieties, so to say, of multiplicative types. So there's at least two types, somehow large classes of algebraic symplectic manifolds. There is some kind of additive type. It's more or less like cotangent bundle of something. So, and the form looks more or less like some dpi, dqi.
This is exact.
It doesn't mean that it's exact, but at least you can write it like this. And of course, if it is t star x, then okay. So in particular, on the level of Poisson brackets, it will be like this: the aij. So in some natural coordinates, it's a constant bracket. Constant bracket. So, and the Nakajima Krieger varieties are of this type. Let's put it like this. Of this type. And the so-called multiplicative type. So it's like symplectic torus. So it's like start to end, and the form would be some log di. So I think it can be algebraically exact. And then on the level of Poisson brackets, something like this. The aij, quadratic, brackets with another quadratic. And the local systems, because there is a group involved, so the global group, so it is of this type. So what we can do is that this variety, I already erased the Krieger variety, so there have been introduced a multiplicative analog of those by Yamakava, and this is those multiplicative functions that I will relate. Exist. Multiplicative versions of n-gram produced by Yamakava. So I will partially recall them later, and because they can be related to local system spaces. Okay, so now what we now want to do is to discuss certain generalization of the concept of local system. So local systems have this feature that we have concurrentity for that. So that pairing is a perfect pair. So I want to do something like this, but for singular curves. So let me call this part micro-local sheaves of model curves. So we can be immediately interested in smooth, compact, complex curves. From the point of view of algebraic geometry, then all of this will be applicable. But then it can degenerate into curve, well, a curve which I can draw like this, but I will just draw schematically like this, into nodal compact. So here, of course, for curves like this, non-periodality, naive non-periodality fails. So we can consider local systems for such curves, but they will not form a symplectic variety. And it's not the right concept. So local systems, not the right. But the right concept would be that we have a nodal curve, positive singular, which is embedded into a symplectic surface. Curve, positively singular, X embedded into a smooth symplectic surface. For instance, if a curve is smooth itself, it can be embedded into its own cotangent bound. X smooth. Surface say S. Embedded to S, which is simply cotangent bound. So now, the simplest singular curve would be a curve like this, where we have transversal intersection at each singular point. So this setting, of course, is the simplest setting of deformation quantization. We think of our surface, we think of our curve as being a Lagrangian, and we may need only a small neighborhood of this curve, but it already gives us some extra geometry. So now, if the curve is nodal, then there is some residual structure. The very fact that it's embedded into a symplectic surface gives a residual structure. If X is a node, then the tangent space is two-dimensional. So this has a symplectic form then. We can make a picture, something something like this, so near a point, near a node x, we have two branches, let's call, say, b prime x, and b second x. And we can sort of imagine them like separate, existing separately and identified by this point. So then we have identification of tx b prime x would be identified with tx star of b second x. Let's call it epsilon subgroups. And similarly, if I have tx b second x, they are identified with tx star epsilon prime. And those, because it's a symplectic form, they are adjoint to each other. E prime second x equals minus e prime x. So they're anti-adjoint to each other. So more formally, we can say that a nodal curve has a desingularization in which those two branches become different. So then if I have a curve, something like this, at one point, so here on top, they will become 2 points. Will be x prime, x. So now let's just axiomatize this residual structure. Let's introduce a name. Let's call it duality structure of x. And data of such identifications for any node. So if you have such, so these data are purely local, they're not required to be compatible in any way, because things happen separately at different nodes. So they always exist. And form a connected space. Just product of, so what freedom do we have to get at one point? Practically up to a non-zero scale. We have fixed this in one way, and this fixed in isomorphism. This one is that fixed way. Always exists, and form a kind of connected space. The product of system. So we can say that we fix something like this. So and then we don't want to deal formally with the symplectic surface anymore. We just say that this residual structure already gives us a lot of data that we need to proceed. Let's make it. So this would be a version of the concept of a module of a deformation quantization, except it will be completely elementary. It will not rely on anything at all. So let x c be a normal curve. Be the duality structure. I lost my discussion of Fourier transform, but happily Pierre gave us such a good introduction. I love that sheet. I don't need it. Okay? With duality structure.
mentioned, Feynman mentioned the time of which Fourier
Yes,
transform.
but those are just identifications, yeah. So what I want to say, I want to use this to perform the Fourier transform.
One dimension.
In one dimension, the simplest easy.
You lose the speech.
Ah?
You lose the speech.
And about space, no, what I meant that I should recall a little. Because when I was preparing, I didn't count on this being explained. So, but I lost this page. This is good. Okay. The varieties structure. Then, a micro-local sheet. X is a data. Well, first of all, a perverse sheaf. And tilde on the desingularization. And second, identifications. Let me write like this. I write F tilde. I restrict to B tilde second X. So this is the part, this is the branch, so it's a small branch, small name. X in the branches. So in the desingularization, they become two disjoint disks. So this thing is identified as a part of the data with the Fourier transform of tilde restricted to the parameters. So to Fourier transform, so with respect to this epsilon. To the x. And similarly, the other one, F tilde restricted to the prime x. With the Fourier transform of F tilde restricted to the second. Identifications inverse ratio. So let me make a few comments to this. Here, so first of all, the Fourier transform is not exactly involutive. So as Pierre said, if you have dB coin, so dB coin of V, then it would be a Fourier transform corresponding to V will go into dB coin of V star, and then it has its own Fourier transform corresponding to V star or to dB coin of V. This is not exactly identity. This is the pullback with respect to -1. But and this may cause some confusion before we remember that those two maps epsilon are not adjoint to each other, they're anti-adjoint. So it's naturally required, if you think of everything symplectically, that there is not a problem. So let me do a few remarks here. Because, first remark, because epsilon second equals minus epsilon prime star. So it's okay to require that they are inverse. Second remark, which is a little more seriously, is that this disk, it's a disk. What are the disks? Logic. But they're not exactly vector spaces. So what they right here is a certain approximate to a statement. So let me say it like this. that B prime x till the B second x still are not exactly vector spaces. Well, there are two ways of dealing with this. So one way is to use the Verdier specialization. Again, I'm not sure if Pierre will agree that Verdier is the right name here. Okay, Verdier sample. Verdier. So that would mean that we have, say, from the category of perverse sheaves of the second text, specialization. Perverse sheaves on the tangent space, on the tangent, one-dimensional tangent space. Here. So then here we have well-defined Fourier transform. And we should say that the connection is between the Fourier transforms of specialization. It's one way of dealing with this. And another more naive way of dealing with this would be to say that the space of choices needed to identify this with the tangent space is contracting. We can simply say. More naively, we can say that the space of choices needed to make them into vector spaces. Identify with the tangent spaces. Is contracted. So basically, the second and higher terms of the Taylor series, this are just a bunch of additive groups.
Also, the space of extensions to the multiplicative surface is also contracted.
Oh, yes. It's
Hidden.
Yes, it's kind of hidden. So anyway, that's an extremely simple concept. So I can talk about perverse sheaves, and also I can talk about complexes, because about constructible complexes in the complex sense. C constructible. So version, let me say. So use that's what's called micro-local. Is a C construct. X2. So those will form a triangulated category or DG category, so this form. DG. Triangulated. Let's call it derived n of x. And so Microlocal sheaves for an additive is called n of x. So in this definition, I didn't restrict singularities of the perverse or constructible sheaves. So first of all, then I have singularities at those points. But I can also allow or disallow singularities at other small points. So let me just say. So fix a finite subset. Then of smooth points. And then we have the category dm of xn. consisting of objects which are smooth outside M and nodes.
It's kind of the same if you make a non-contour curve heading.
Yes, yes, yes. I'll actually return to this a little later. Now, our first theorem is this, that if X is compact, so here a priori we don't really require our curve to be compact. Then D M X empty set, which means that we don't allow any other singularities. So is a Calabi-Yau category, is Calabi-Yau dimension. Which means that we have identification of complexes are home from F to G, dual. So this is because we're dealing with constructible sheaves, then it's finite dimensional. But again, as Pierre mentioned before, so there is no Poincare duality, there is no set factor for constructible sheaves. Even if you prescribe singularities, then it's a little awkward to say what will be the set factor, if any. But the statement is as canonically identified to R home. GF shifted by 2. And the proof follows from the local duality from application of Schobers factor mu home. Proof uses local or micro-local duality for mu home. So it does not, if we just work with category of constructible sheaves, this would not allow us to deduce anything. But if we have this property, then it works. So this has to be compared with a purely topological statement and completely elementary. It can be compared with that if X is actually embedded into S, which is a symplectic surface, compact normal curve. So and if AS is a deformation quantization of S, dq of OS, so it would be, so in this setting we work over a ring of field of Lorentz series in the Planck constant. And that's then the category of AS. One, so support inside X is Calabi-Yau of dimension 2 in this case because it's a surface. And this can be found in Schobers-Shapiro open deformation quantization. So in this case, it will follow eventually from the set duality. If we look into what's happening here, so this is the deformation of OS. So there's a set duality in degree 2 for OS, and this is certain lifting of this. And here we have Poincare duality on basically Poincare duality on the singular curve. So the moral of this is that that micro-local sheaves, in this sense, are exactly a good replacement for local systems from smooth curves to singular curves. we could replace it. Local systems. For model curves. Oh, what do you mean? So this doesn't have to be globally inverted at all. We just take symplectic structure of any two-dimensional tangent space. In order to define the concept of micro-local shift, but
The curve doesn't have to be global.
what do you mean plan?
Relatively.
No, here, yes, at least I don't know how to say anything more general. I simply don't know. I think we need here a symplectic surface. We need some neighborhood. Yes. Well, so in fact, I think what you're saying, it pertains, as they say, to the meaning of this AS mode, to the gluing of this category in terms of local patches. Of that this is a sort of mode. You may have a surface, but even then you don't have a standard shift frames and so on and so on. Okay, let me now work out one example. Consider the simplest model curve, which contains of two copies of P1. P1, with coordinate x. So let's just one P1 and another P1. So called x prime. This would be P1 and x. So then the singularization x tilde is simply the disjoint union of the things, but which we don't want to identify. So what is the data here? We will have a perverse sheaf f second here and perverse sheaf f prime here. So this perverse sheaf, so in a disk, so let's look at the disk would be x tilde second, would be x tilde prime, that would be the disk, would be b tilde second. This would be a disk called b tilde. Okay. So on this disk b tilde prime, f prime given by a map, say phi psi and two maps. So phi prime psi maps. On the other one, the second would be another thing, phi second, psi second. The fact that they are related by the Fourier transform means that they identify like this. The psi for this identified with phi for this, psi for this identified with psi for this. So this is the Fourier transform. So really we have only one sheaf. So basically what we have one sheaf here, and whatever is here is simply Fourier transform. Right? But now we have a sheaf more than just on the disk. We have the sheaf on P1. So what does this mean? It means that around infinity there is no monogram. So because f prime extends to P1, its monogram with respect to C, which would be 1 minus, let's say, so let's call this A and let's call this B. 1 minus AB is equal to 1. So therefore, AB equals 0. So because the second one extends to P1, so its monogram with respect to psi second, which is the monogram of the original one with respect to phi prime, equals 1. And this means that BA equals 0. So we found that that such microlocal sheaves are given by pairs of vector spaces and maps in both directions, such that, so let me write like this, M X is a set, it's a category of diagrams. I write phi psi, A and B, such that AB equals 0, BA equals 0. And this is precisely representations of the pre-projective algebra for the quiver of these two vertices and one angle. What representations? Pre-projective algebra for the quiver like this. So now here is the standard pre-projective algebra. In fact, what happens here, that the multiplicative version of this algebra will be the same as this additive version, but in general it will be different. So let me now discuss multiplicative pre-projective algebras. So and this was done by Curly Moller. And by Yamaka. So this exactly matches this the dichotomy of additive versus multiplicative symplectic manifolds. So you will see the formula, how they are modified. So gamma is equivalent as before. So when I say algebra, so this algebra is distributed in the sense that there are idempotents corresponding to the vertices of the quiver. So it's better to say that there is a linear category. Let's say we will associate a C-linear category lambda of gamma with objects would be the set of vertices. So, and as in the ordinary pre-projective algebra, for every arrow, we have two generating morphisms. Would be so the source of H and the target of H. This morphism would be A sub H, this morphism B sub H, subject to relations. And then we look into the relations, we realize that they simply cry to notice that they're dealing with perverse sheaves. Subject to relations. So first relation, that 1 minus AH BH, 1 minus BH AH are inverse. So strictly speaking, one say it's not a relation, it means that we end formal inverses. Or we consider representations, we care only about those representations in which they are inverted. And condition number 2 is just almost literal multiplicative rewriting of the relations for original pre-projective function. I write product over arrows which terminates at I. Here I write 1 minus AH times product over edges that begin at I, 1 minus BH AH. And this is supposed to be equal, and then again there is a version when there is a constant. So can put on this, a family of algebra depends on the choices of those constants. No, so far I didn't say anything about that. I'm talking about pre-projective algebra. Right? So now there is one thing which I sort of didn't say yet. So those are non-commuting operators. So when I say product, I mean I multiply them in some order. So here we implicitly imply that assume that we have chosen a total order on the set of errors and multiply everything in this order. Here we assume chosen total order this E and multiply in this one. But now the first statement of this theory is that this category up to isomorphism is independent on this choice. It's not. Lambda gamma is up to isomorphism. Independent of this choice. Now if you look at what this gives us for this quiver, it's precisely the same. So for the simplest non-trivial quiver, the same as additive. In general, it will be slightly different. Somewhat actually substantially different because of this. But sort of relation is a little bit like between the group and the Lie algebra. So now our second theorem is this, that suppose X is, so how to relate the two constructions? Suppose our curve is glued out of projective lines. So every component of our little curve is a P1. Then up to topologically, the datum is the graph which describes how those P1s intersect. So let's assume that all components X, so X along the curve, are wrench. Which components are Xi as a model of P1, and I from some. And graph of intersections. It's gone. It's some orientation. So now another part of this theory is that it is independent on the orientation. And on orientation. So then the category of micro-local sheaves is simply identified with the category of representation of that algebra. M of X set is equivalent to that. So let me say how it is. No. Lambda gamma is a linear category with finitely many objects, which we sort of simply say it's an algebra. Now it has representations, which means functors from this category. So the definition is functors from lambda. I write lambda gamma. Lambda gamma, which actual assignments of vector spaces to so explicitly, such an assignment, so it would take each object I, take to some vector space E. Right? So the I, corresponding to a microlocal sheaf F here, is the stock of F, stock of F at some chosen point. That we call yi. Take one point on each point. And the proof is, again, elementary. We look at the local description in terms of field psi, and get this simply by translating the condition that the monodromy on the projective line of a local system is equal to 1. So look at local. Some descriptions. And express fact that product monodromy is into 1. Now this is actually at this point it's kind of interesting to compare this with the corresponding raft category. So it's so if it's a symplectic situation, then so formally at least it's understandable, and there is a paper of Ed Gill, called causal duality functions in Floyd theory. One day, studying the rational category, but they get a little different answer, more like an of additive nature. So their answer of more additive rather than multiplicative nature. So presumably that can be that is hidden in the use of causal duality, and presumably it can be brought in a more direct relation by doing it more systematic. So they get more or less the additive. In this case, they get more or less. Yes. Well, probably I agree if it's done properly. Yes. It's complete. It's completion. It's completion. It's causal duality. Yes, and from this, they may also have wanted to bring it to something known, something more familiar. They probably didn't know. Yes. Yeah, but that was sort of. Yeah. Okay, so now let me discuss more general multiplicative Query varieties. So again, we consider diagrams as before with V and W. So once we have this, we got this formula which was on this previous board, right here, so that's some traces. With the product, since it's basically done exactly like this. VI, VJ, AIH, DH, J. So with the relation that everything which we can conceive of is irreversible, and 1 minus AH, 1 minus DH, AH, 1 minus UI, I, 1 minus DI, that's irreversible. Plus relations which I want to call the group valued moment map relations. It will be 1. It's the same, minus UI is the I. So the other thing would be just as before, product. I, 1 minus BH. Minus 1 equals 1 or some constants. Again, so this is considered plus some stability condition and modular GLV. So plus some stability. It's in modular GLV. So then the geometric point of view on this would be to consider microlocal sheaves, but with singularities at some other points. And those would be the vanishing cycles at those singularities.
Suppose it uses several W which equals to 1P.
That's possible.
Yeah.
Yes. So what I'm saying, yes. So let me. So in this way, yes, we can get more general things. So let me discuss the framework. Yes. So geometrically, you should consider perverse, that's microlocal sheaves. In M of X n, and maybe not empty. Plus rigidification or sort of identification of vanishing cycles. Plus identification of vanishing cycles. Cycles say they feed. Sorry, psi. Phi x f. So this is a new small point x and f. With some spaces double it. So geometrically it means when we allow new points, it means that we even if our curve was compact, we add here non-compact cotangent phi. T star x. So and then the curve, even if it was compact, the new thing will be not compact. It will still have canonical sort of identification of tangent spaces. So again, we get a new curve, a new normal curve. Wow. So then we can say that m of x m is the same as m of y and nothing. But if this was compact, this will be non-compact.
But anyway, so if you choose, so here we choose vector spaces W with X. W with X. And consider such data. So if you fix this, they cannot form a linear category because they fix this. So, but we can form the modular stack of such objects. Modular isomorphisms are identical on W. Let's call M W of X M equals modular stack of such objects. Such data. Modular isomorphisms identical. So this makes sense, actually, even when the curve itself is smooth. So in this way, we get some interesting generalizations of linear varieties, which don't even require the concept of micro-local sheaf. So X smooth compact is okay. And interesting.
Surface with boundary, and on each boundary component fix one point and trivialize the part of this point.
Yes.
Yeah.
This is more like yes.
Yes,
Absolutely. That's you're absolutely right. Actually, this is how I actually do it. Yes. Okay. So let me keep this. So now, at this point of view, at this situation, and that probably was the reason why multiplicative pure varieties were not known more widely, is that there are, as such, they are not symplectic. In fact, they are instances of the situation known as the group value, as I said, group value moment map, introduced by Alexeyev, Malkin, and Meyer. So, and this also goes into under the rubric of systematically analyzing symplectic manifolds or of multiplicative type. So usually, so what's the moment map? So usually, a group acts in a Hamiltonian way on a symplectic manifold, called Hamiltonian function. And it gives the moment map mu from M to the dual Lie algebra. And the reduction, the Hamiltonian reduction, equals usually something like this, preimage of 0, modular. In particular, it's a property of this that it's invariant under G, and so on. Now, if G is effective, so the Lie algebra is identified with this dual by the scalar product, which I already mentioned. So we can think in a perverse way that the moment map takes value in the Lie algebra and not in the dual, as we can view. Mu is a map from M to G, and we can try to write the relations, the conditions, in those terms. So now, and this is what the multiplicative theory does. It passes from the Lie algebra to multiplicative group. So we consider the following situation, and this is called a quasi-Hamiltonian G space. is a dictum consisting of, first of all, we have a manifold M, and a two form, omega 2 of M, which may be not closed and degenerate, possibly closed and degenerate.
Non-closed.
Possibly non-closed. Yes, sorry, yes. Non-closed and degenerate, yes. With the group, with the reductive group acting on this. And with a map called M, known as the group value moment map, taking the value in the group. So now the scalar product gives a three form on G. Three form that's called eta on G. The closest there is a so this is another sort of perennial subject that any compact group, any reductive group has a three form which is a germ, and so this germ appears in many ways. For instance, it can be written like this. Normalization is 1/2. Here I write like this. I have so about G minus 1 dg bracket with G minus 1 dg, G minus 1 dg. Where G minus 1 dg is a minus 1 dg is a form omega 1 on the group, the values of the level. But in this we get the three form. Also there is also a form dg times G minus 1. The left and right invariant Maurer Kapranov forms. The same with properties. So first, I say that it is not necessarily closed. So the differential of omega is the pullback M star of E. Secondly, I said that it may be degenerate, and the kernel of this form, kernel of omega at the point x, is a span of some vectors. Let's go like this. So if the group acting, then every psi in the Lie algebra gives me a vector field x. So it is. So I just it reproduces here is a span of values of d psi of x, for which psi lies in the kernel of R M of x, which is anti-invariant space. And there is a third space, and there is a third condition, which is sort of gives me the compatibility between two structures, that for every psi in G, the contraction with respect to d psi omega is equal to 1/2 pulled back. So it would be two form, we're going to be one form. And here I get, now let me get the scalar one form. I get G minus 1 dg plus dg times G minus 1. This is a vector form. This is a one form lying in the algebra. I take the product, etc. So in this case, so it doesn't maybe not symplectic at all. So in this case, the theorem of, let's say, Malcolm and Marenkin, that the quotient M minus 1 of the identity of G, this is a symplectic in the honest sense, or provided under the usual assumption that it is smooth and so reduction is honest symplectic. So now our statement is that this space, so this space is a quasi-Hamiltonian space. So the group, so here the group GL double X, and this is a quasi-Hamiltonian space. In particular, it's not necessarily symplectic. So that may be the reason why multiplicative pure varieties are not known so widely. Because it's not symplectic, so we can do anything with that, supposedly. But no, so if you look at this systematically, then it's very useful concept. So our theorem that m double xn is a quasi-Hamiltonian. GLW space. So in this definition, the moment map is a part of the structure. So in fact, here, when we say it's Hamiltonian action, it means that we can choose Hamiltonians. So in a way, so that this is a part of the data of a Hamiltonian action. So similarly here. So it's a quasi-Hamiltonian GLW space. So the moment map, the group value moment map, is given by the monotonous on the vanishing cycles. X and the portion would be the corresponding modular space of objects in this curve y I explained before, but we compactify it at infinity and then look now. So the result of compactifying y infinity of q. So and now to get multiplicative pure varieties, we should do the same thing as we did for pair-projective algebras. We get we take x equals x gamma, equals union x I equals p1. Take n to be at just 1 point. 1 point. Say, of the I in each xi. So in this setting, we can take many points. But if you just do this, so then we can say that m gamma multiplied with double parameterizes. Yes, that's Micro-sheaves. Phi x, phi zi, identified the double. So in particular, this is a quasi-Hamiltonian space. So it's not symplectic, but it will become symplectic if we do the quotient, and one can say what happens if we do the quotient. Oh, okay, so I'll probably stop here. Thank you very much.